I have always questioned whether people really have their future planned out for them or not, or if the decisions they make every day lead to different outcomes. Up until last year, I discovered the butterfly effect, and it is something I have been intrigued with since. But as many people have misinterpreted the butterfly effect, like myself, in which a small change creates a big event somewhere else. However, the butterfly effect is actually about approximations, as I have now learned while working on this project. Because of my interest in the butterfly effect, I wanted to see if there was any math involved, and today I will be explaining chaos theory and how it ties into the butterfly effect using weather predictions as an example. In 1972, Edward Lorenz asked whether the flap of a butterfly's wings in Brazil can cause a hurricane in Texas. Edward Lorenz's idea of the flap of a butterfly's wings revolved around the central concept in chaos theory called sensitivity on initial conditions. An example of the system is called a double pendulum. A double pendulum is simply two pendulums attached end to end.
The motion of a double pendulum is highly dependent on the starting position. Due to the erratic behavior, different starting positions lead to very different paths. Sensitivity on initial conditions means that starting the pendulum in a slightly different position would cause drastically different behavior. And the double pendulum is also an example of something called a dynamical system. And you can think of a dynamical system as simply a point in space, and as time passes, the point moves around.
Chaos theory deals with non-linear things that are effectively impossible to predict or control, like turbulence or weather. A guy named Patrick Young once said that the trouble with weather forecasting is that it's right too often for us to ignore it and wrong too often for us to rely on it. Edward Lorenz developed a set of equations to model a simplified weather system. Here are the three equations that he developed, and here we have dx over dy is equal to theta of y minus x, and dy over dt equals rx minus y minus xz, and the third equation is dz over dt is equal to x times y minus b times z. The equations model the flow of fluid, which is particularly air, from a hot area to a cold area. The solution of the set of differential equations is a dynamical system. We can plot the solution with varying initial solutions.
My main focus today isn't very much on the Lorenz equations. However, when I do plug in the starting points to get the solution that is right at the top, I get this as my graph.
This plot is sometimes called the Lorenz butterfly due to its shape. This plot seems to spiral around two distinct points, and the 2 points are called strange attractors. And basically what this means is that we cannot predict when a solution will jump from one attractor to another. When given another solution, for example, if each coordinate on the initial condition has been scaled by 10%, the solution may appear to be smaller to the original, but it's quite different.
If we were to graph the distance between the two solutions, we can see that initially the distance is relatively small. However, it eventually becomes large and completely unpredictable. This is yet another example of sensitivity on initial conditions. We see similar behavior if we reduce the disturbance to 1% and 0.1%, because although the period where the error is small, it lasts much longer. However, once the error jumps once, it is just as unpredictable as with the first distance.
When we plot all four solutions simultaneously, we can see the small differences between them.
It is this sort of sensitivity on initial conditions that makes weather predictions difficult to predict. In this graph, the red corresponds to the period of time that we are able to accurately predict the weather, which is usually 5 to 10 days. When we change initial conditions a tiny bit, they make a great difference.
So because of the sensitivity, unless we perfectly describe the initial conditions, which is impossible, predicting conditions and the long term is also impossible.